Welcome to this explainer. I'm so glad you're joining us today because we're going to unpack something really incredible. One of those modern miracles that's totally invisible but runs our entire world. Usually when we think about the Internet of Things, we picture the flashy stuff, the smartwatches, the connected thermostats, maybe even self-driving cars. But underneath all that slick hardware, there's this staggering, high-stakes logistical puzzle. Think about it for a second. How exactly does a tiny remote sensor out in a farmer's field securely fire off data to a cloud server halfway across the planet in literally a fraction of a second? Well, today we're going to demystify the invisible post office making all of that possible, the IoT network layer.
To really wrap our heads around this, we've got to talk scale. It's massive. Experts forecasted that by 2020, we actually crossed a threshold of around 50 billion connected devices. 50 billion! Just imagine trying to run a literal postal service where 50 billion people are frantically mailing millions of letters to each other every single second of the day. Without an absolutely flawless, globally agreed-upon addressing and delivery system, there'd be no Internet of Things. We just have total digital chaos.
And hey, it's not just the sheer number of devices that's wild, it's the variety. We're looking at a vast ecosystem that includes everything from heavy factory machinery and smart city infrastructure to the fitness tracker on your wrist and the smart thermostat in your hallway. I mean, a heart rate monitor doesn't naturally speak the same language as an industrial robotic arm, right? Yet they share this exact same digital ecosystem, so they absolutely require a universal set of rules, a baseline protocol, to communicate and actually make sense of the data they're swapping.
So here's our roadmap for this explainer. First, we'll look at the IoT network layer itself. Second, the address book crisis. Third, how 6LoWAN saves the day for small devices. Fourth, we'll move up to the transport layer. And finally, number 5, we'll compare TCP versus UDP.
All right, let's dive right into number 1, the IoT network layer.
Think of this as the foundation, the grand sorting facility of our invisible post office. The network layer has one very specific, monumental job: transferring data, or what we call IP datagrams, from a source network directly to a destination network. It's basically the ultimate routing logic for the Internet. Its primary functions boil down to 3 things: host addressing, packet routing, and inter-network communication. Basically, every single piece of data gets bundled up into a packet. The network layer slaps a source address and a destination address right on the front, and then it calculates the absolute best path to route that packet across multiple interconnected networks so it arrives exactly where it's supposed to.
Which brings us to part 2. The address book crisis.
So as the Internet of Things just exploded in popularity, our digital postal service hit a massive bottleneck, a real existential crisis. See, for decades, the Internet ran on IPv4, Internet Protocol version 4. It uses a 32-bit addressing scheme, which means it can generate a maximum of about 4.3 billion unique addresses. Now, back in the 1980s, 4.3 billion sounded like an infinite number. But remember that scale we talked about earlier? 50 billion IoT devices? So the IoT boom rapidly exhausted that IPv4 limit. We literally ran out of digital mailing addresses.
But no need to panic, because the solution was IPv6. Engineers realized we were out of room, so they deployed Internet Protocol version 6. Instead of 32 bits, it uses a massive 128-bit addressing scheme. That gives us roughly 3.4 times 10 to the 38th power of addresses. That's 340 undecillion? It's a number so mind-bogglingly huge that you could assign an IP address to every single atom on the surface of the Earth and still have plenty left over. It's wild. IPv6 was designed specifically to handle the staggering, hyper-fast growth of large-scale IoT deployments.
Moving on to number 3, 6LoWPAN for small devices.
Okay, so we fixed the address book, right? Well, kinda. We actually created a brand new problem. IPv6 addresses are huge and complex. How on earth do you get a tiny, battery-powered sensor to process such a massive address? Enter 6LoWPAN. It stands for IPv6 over low-power wireless personal area networks. Total mouthful, I know. But the concept itself is beautifully elegant. It basically acts as a translator. It enables those low-power devices with very limited processing power to actually use IPv6, taking that massive address and making it manageable so it doesn't instantly kill their tiny batteries. It's custom-built for these constrained IoT devices that have to operate in super low-power environments. It also supports communication over IEEE 802.15.4 networks.
Basically, by doing all this clever compression behind the scenes, 6LoWAN enables true internet connectivity for the smallest embedded devices out there. It perfectly bridges the gap between the heavy-duty internet and the ultra-lightweight world of microsensors.
Let's step up to part 4, the transport layer.
So, the network layer addresses the package. Now what? Well, the transport layer acts as our fleet of delivery trucks. This layer is what actually provides end-to-end communication between devices and applications. It's the logistics manager. Its main functions include segmenting large messages into smaller, manageable chunks, doing error control to ensure nothing got corrupted along the way, handling flow control so a fast sender doesn't accidentally overwhelm a slower receiver, and managing congestion control to keep the whole network from getting jammed up.
And finally, Part 5, TCP versus UDP.
When you mail a package in real life, you usually have to pick your service type, right? Like, do you want it fast and cheap, or do you need it certified and guaranteed? In the IoT world, that choice usually comes down to two main protocols. First, we have TCP, or Transmission Control Protocol. This one is connection-oriented. It actually establishes a formal connection before it sends a single byte. It provides highly reliable communication, ordered packet delivery, error detection, and even retransmits lost packets. It's very thorough. Then on the flip side, we have UDP, the User Datagram Protocol. UDP is connectionless, no setup required. It just starts firing data. Because of that, it has very low communication overhead and incredibly fast transmission. But the trade-off is that it doesn't guarantee delivery, doesn't care about packet ordering, and doesn't eliminate duplicates. It's totally stateless.
To put it simply, TCP is the certified mail of the internet, is what you use for HTTP, HTTPS, sending emails, or transferring files where you absolutely cannot afford to lose any data. But all that reliability requires a heavy processing overhead. UDP is more like the standard post. It's blazing fast, very lightweight, and perfectly suited for time-sensitive IoT devices. Think about a smart thermometer sending a temperature reading every single second. If one tiny UDP packet gets lost in the mail, who cares? The next reading is coming a second later anyway. UDP lets these lightweight devices communicate at top speed without the heavy burden of setting up connections.
When you put all these pieces together, from the addresses to the delivery trucks, you get incredibly sophisticated setups. Take an IoT Level 6 architecture, for example, which uses a centralized controller. You've got multiple monitoring nodes at the local level, seamlessly firing data up to cloud analytics components. And that centralized controller can shoot commands right back down. All of this high-level communication relies on the flawless operation of that underlying network and transport layer we just explored. It's the invisible post office working tirelessly at lightning speed. We've come a long way, right? From totally exhausting our digital address book to inventing a virtually infinite new system and then tailoring the whole thing for the smallest, lowest power devices on Earth. But, innovation never sleeps. As we push toward entirely smart cities and real-time autonomous systems, we have to wonder, as we deploy billions more of these low-power sensors, what happens when even our current fastest protocols just aren't fast enough? How is the invisible post office going to evolve next? I hope this explainer gave you a powerful new lens to look at the IoT networks constantly buzzing all around us. Keep questioning, keep learning, and we'll catch you in the next one.